Hello guys, welcome back to Foolish Engineer YouTube channel. Imagine you are carrying around a power bank that charges your smartphone, smartwatch and even wireless earbuds with all different voltage needs without a problem. Do you know who is doing that? Well, you guessed it right, a bidirectional buck-boost converter. And today we are taking a deep dive into the circuit and its working. So let's start. One of the key reasons I started this YouTube channel is to bridge the gap between outdated Indian education system and actual skills needed in the industry. I'm excited to share that this video is sponsored by Altium. If you're an electronics student in India, you can get Altium Designer for free under its Altium Student Lab program. It is an advanced electronics hardware design platform. It's a fantastic way to enhance your skill and increase your chances of landing a job in core electronics companies. And with its best feature, Altium 365, you can upload projects to the cloud, manage libraries, collaborate, and review with your team. It supports all CAD files, making an electronics design faster and easier. Just use your university email to get started. Plus, you'll receive a student license, a PCB design course, and a certificate recognized by top Indian industries. You also get a free access to Power Analyzer by Keysight. I've personally used Altium Designer since the start of my electronics journey, and I really recommend it. So don't miss this chance. You can get started with Altium 365 by clicking the link in the description. Last time we saw the USB power delivery, and that's where we saw the need of a buck-boost charger. What exactly is a bidirectional buck-boost converter? Think of it as like a two-way street for electricity. It's a circuit that can either step up or step down the input voltage, and here's the cool part, it can do this in both directions. To understand how a bidirectional buck-boost converter works, let's think of it as a cyclist navigating a hilly road. In buck mode, the converter is like the cycle shifting to a lower gear when going downhill. This reduces the cycle speed so that it can descend a hill without losing control. Similarly, the converter steps down the voltage to a low level to charge the devices with lower voltage requirements. On the other hand, in boost mode, it's like cycle is shifting to a higher gear to climb uphill. Here, the cyclist is increasing his pedaling effort to overcome the resistance of the hill. Just like the converter steps up the voltage to power a device that needs a high voltage than source can provide. Now imagine this bicycle rider can instantly switch gears back and forth, adapting to the terrain. This is exactly what a buck-boost converter does. It seamlessly switches between stepping up and stepping down the voltage depending on the requirements. Now we'll see the working of this circuit with an application. Let's assume a circuit of battery charger which gets charged by the charger, and later on it charges the phone, smartwatch and headphones as well. This is where a bidirectional buck-boost converter works. The circuit is designed to operate in both charging and discharging mode, depending on the voltage levels of the charger power supply, also called as DC bus voltage, and the battery. This basic circuit consists of 4 switches: Q1, Q2, Q3 and Q4. These are the MOSFETs which control the direction and mode of the converter. Then inductor, which stores the energy temporarily and releases it to boost or buck the voltage. After that, we need input and output caps and its control circuitry. There are 6 different modes of this converter, and these work as synchronous buck converter, synchronous boost converter and a synchronous buck-boost converter. It also works the same when the current is flowing in the opposite direction. The converter uses these four switches to manage the power flow. Two switches get active in buck or boost mode to reduce the switching losses, and all four switches are used in buck boost mode to efficiently handle power transfer when the input and output voltages are close. Second is the charge mode operation. Now let's see the charging operation. The converter charges the battery when there is power available from the DC bus. Depending on the relative voltage of the DC bus and battery, the converter operates in different modes. First mode is when the DC bus voltage is greater than the battery voltage. Then this converter would act as buck mode. So during this time, Q3 is fully turned on, Q4 is fully turned off, Q1 and Q2 are controlled by PWM signals, where Q1 operates with duty cycle D and Q2 operates with duty cycle 1 - D. This configuration steps down the voltage from DC bus to the battery, similar to a buck converter. If you look closely, this circuit looks like a synchronous buck converter with two switches, an inductor, and input-output capacitors. We have already seen how this buck converter works in this old video. You can check by clicking on the card above. The converter draws power from the higher voltage DC bus and helps it down to charge the battery. When Q1 is on, the current flows through it and inductor charges. When Q1 turns off and Q2 turns on, the energy stored in the inductor is released to the battery, providing the same output voltage. Next charge mode is when the DC bus voltage is less than the battery voltage. Now we'll see how this circuit works to charge the battery if the DC bus voltage is less than the battery voltage. This time Q1 is fully turned on, Q2 is fully turned off, Q3 and Q4 are controlled by PWM signals, where Q4 operates with duty cycle D and Q3 operates with duty cycle 1 - D. This circuit steps up the voltage from battery to the DC bus. This is the synchronous boost converter. When Q4 is on, inductor charges with the current from the DC bus. In the next cycle, Q4 turns off and Q3 turns on. The stored energy in the inductor is transferred to the battery. Now you might be thinking, what if the input bus voltage is nearly equal to the battery voltage? In that case, Q1 and Q2 are controlled by duty cycle D, where Q2 and Q3 are controlled by duty cycle 1 - D. All four switches operate in a coordinated manner, allowing the converter to function in buck boost mode. The converter logic controls the circuit seamlessly, transitioning between buck and boost operations when the input and output voltages are nearly the same. Next is the discharging mode. The converter discharges the battery to supply the power to DC bus. Here also, operation mode changes depending on the relative voltages. First is when the DC bus voltage is greater than the battery voltage. So this time Q3 is fully turned on, Q4 is fully turned off, Q2 and Q1 are controlled by PWM signals, where Q2 operates with duty cycle D and Q1 operates with duty cycle 1 - D. This configuration steps up the voltage from the battery to supply the DC bus, so this is the reverse boost converter. When Q2 is on, the inductor charges from the battery current. When Q2 turns off and Q1 turns on, the stored energy in the inductor is released to the DC bus. Now, if the battery voltage is higher than the DC bus voltage, then this circuit would work as a buck mode. So here Q1 fully turns on, Q2 is fully turned off, Q3 and Q4 are controlled by PWM signals, where Q3 operates with duty cycle D and Q4 operates with duty cycle 1 - D. This setup steps down the voltage from battery to supply the DC bus. So this is the reverse buck converter. When Q3 is on, the inductor charges with current from the battery. When Q3 turns off and Q4 turns on, the energy in the inductor is transferred to the DC bus. And finally, if the input bus voltage is nearly equal to the battery voltage and current is supposed to flow in this direction, then Q2 and Q3 are controlled by duty cycle D, Q1 and Q4 are controlled by duty cycle 1 minus D. All four switches operate in a coordinated manner, allowing the converter to function in buck-boost mode. The converter adjusts its mode dynamically between buck and boost, maintaining the output voltage and supplying current efficiently. Now let's see where these converters are used in real life. First is renewable energy systems. Think about solar panels on a cloudy day. The output voltage fluctuates based on the sunlight, and a bidirectional converter can adjust to these changes, stepping up the voltage on a sunny day and stepping it down when it's cloudy, ensuring a steady output. Or in portable electronics for devices like laptops and smartphones, bidirectional converters maximize battery life by efficiently managing charging and discharging cycles. Let's weigh the pros and cons of using bidirectional buck-boost converter. The converter minimizes energy waste and maximizes performance, which provide very high efficiency. This circuit is very versatile. Just like a Swiss Army knife, it can adapt to various situations and power levels. And it's very compact in nature. But there are few challenges to it as well. It needs complex control algorithm to manage the power flow. High efficiency comes at a cost, so heat management is also an important factor here. And there you have it. This is all about the basics of bidirectional buck-boost converter. If you enjoyed this video, give it a thumbs up and don't forget to subscribe for more powerful content.